All right, thank you, Sherry. Leading off this inning, we have Prashant Anantharaman. He is a third-year student here in the Trust Lab, a first-year PhD, and he's going to talk about scalable identity and key management for publish-subscribe protocols and what we can do to make them feasible in energy delivery systems. So, Prashant, the floor is yours.
Thank you, Dr. Reeves. Firstly, this work is joint work with Karthik, Elizabeth, Professor Nicole at Illinois, Jason, who just introduced me, and of course my advisor Sean Smith. So in this talk, I'm going to first introduce what publish-subscribe protocols are and talk about our contributions over there, and also talk about, and then go on to talk about what our architecture is, what our proposed architecture is, and then also describe our implementation and discuss some preliminary results. Okay, so what are publish-subscribe protocols? So publish-subscribe protocols are protocols where there are producers and consumers. The producers publish messages on specific channels, and consumers consume them on these channels. The consumers subscribe to specific channels and then consume them. And the routing of these messages happen through a broker or a server, in other words. And all the purpose of the broker in some cases is also to do authentication, but it's usually just to perform routing and keep track of which consumers subscribe to which channels and forward these packets as it is. So we did some preliminary study on Shodan, and we ran some preliminary searches on Shodan, and we found that there were plenty of implementations of MQTT, AMQP, Stomp and Stomp on the internet. And we also studied this other protocol, which is a subset of 61850 called Goose. And the thing is that it's an Ethernet layer protocol, so we cannot really run Shodan searches to find them on the internet. So this is how a subscription happens. So an administrator actually subscribes to the pound symbol, which actually means that the administrator is subscribing to all channels on a particular broker, and the actuators and sensors and the other devices subscribe to device-specific channels, and they are only concerned about specific channels that they need to listen on. And when an administrator wants to publish commands to actuators, the administrator publishes them and sends these messages to the broker, and the broker forwards it as it is to the particular actuators. And the exact opposite happens when sensor data is being received to an administrator from the sensors, where the sensors publish data and the broker forwards them to the administrator. So the industry partners that we have are making use of MQTT as a scalar protocol. They are using it in smart meters and in grid control. And from our conversations with our industry partners, they acknowledge that the MQTT protocol and its implementations have several issues. And we will talk about that in the next slide. But then, so one of the so as you can see from our scan, there are several of them in China and in the US. So the protocol, the biggest issue is that there is no way to identify a sender in the MQTT protocol, and from previous work, there are no real key management solutions. Most of them talk about lightweight crypto solutions, but none of them talk about key management or revocation. MQTT protocol during connection responds with a connection code, and the connection code tells us whether the connection was accepted or if the server does not want us to connect to that particular server. And we ran this scan again using Shodan, and we found that 69% of them actually just accepted connections from Shodan as it is, without any authentication or without any client-side certificates. As you can see, 10.5% of them did not allow us to connect because it required a username or a password, and 19.5% of them required a client-side cert and did not authorize the connection. So the Goose protocol is an Ethernet layer protocol, as I said earlier, and the Goose protocol is actually susceptible to a lot of attacks, including the replay attacks and spoofing attacks. And these primarily originate from the fact that it's an Ethernet layer protocol, and hence it is susceptible to all the attacks on the Ethernet layer protocol. One big issue from that we discovered in the protocol was this, that the sequence number field. The protocol specifies that the sequence number has to be incremented continuously, and if you receive a sequence number that is way higher than the previous sequence number that you received, or if an attacker spoofed a message with a way higher sequence number, then all the messages that are received within sequence number lesser than the spoofed value are all ignored. So here are our contributions in this work. So we provide results from measurements, and we demonstrate the effectiveness of our macaron-based key management scheme, and also we built an entire toolkit for our scheme and demonstrate in terms of developer effort and CPU time that our scheme is within the acceptable latency bounds, and it is effective. Okay, so first I want to specify the goals for our system. So we want to make sure that the system is resilient to active server compromises, and we assign separate keys for long-lasting assertions like identity and short-lasting ones, which prevent accesses to channels to clients that shouldn't be accessing. And we also want to make sure that in case of a device compromise, only the channels the device has access to can actually be are subsequently compromised, and not the entire system itself. We also assume that the keys can securely be deployed to a device, and we are making use of cryptographic primitives in our system, so we want to make sure that they are bug free, and we also assume that the devices can securely store these values. And of course goes without saying that we are not addressing side channel attacks in this particular scheme. And so in our approach, we are talking about two different kinds of identities for each particular device. One is the core identity, which is installed during deployment, and the other is the set of association attributes, which are basically one macaron per each channel. And these are shorter lived and need to be changed frequently. I will get to what a macaron is in the upcoming slides. So an attribute is actually formalized as a tuple, and where we are talking about a property P that holds for object O for a time delta, and these attribute assertions are made by the controller, and the core identity assertions are made by a deployer during the deployment phase. So what is a macaron? So a macaron was a technique that was developed by Google, and it consists of two parts, and there is a public part that consists of a random nonce and a set of caveats. That is what you see on the right hand side of this image. The nonce, the validity, and the recipient are the ones that are the public part of the macaron, and the one on the left hand side, which is the initial key that is used to construct the first HMAC. And the HMAC algorithm is run iteratively on each caveat, and then the final HMAC, which is K2 over here, is the shared secret between the client and the server, and the values K1 and K2 are kept as a secret over here. So this is the algorithm to generate a macaron, where we talk about a random nonce, and then we talk about the device ID itself, and then we talk about the manufacturer or the deployer, and we iterate over the set of caveats, and then we also have a timestamp that specifies the expiry of the macaron. So how are macarons actually a parallel to PKI itself? So in PKI we have a root private key that is used to create which is basically an RSA key pair, and then it is used in the RSA algorithm. And there is also a root public key which is publicly known to us. So as a parallel over here, the public part of the macaron is publicly available to everyone, and it is actually transmitted in plain text also in our scheme. But the secret cannot really be computed without the initial root secret key in terms of a macaron. And macarons also allow the same sort of chaining that are allowed in case of PKI. Now let us start talking about our scheme. So in our scheme, we basically have a bunch of phases. Initially, there is the setup phase, where the device is installed with our identity macarons, and then they are connected to the network, and the network and once the device is connected to the network, the device negotiates session keys with the controller, and then the session keys are negotiated, and the device says which channels it needs to connect to, which is again specified in the identity macaron, and then the controller then gives the set of channel specific macarons to the device itself, and then the device is basically in operation. And when so these keys are also short-lived. So then once these channel specific keys are revoked, the device has to renegotiate them with the controller at the end of this expiry. So who really can make these assertions? So in our case, the controller basically makes the assertions to a bunch of manufacturers or deployers, and says that they are authorized to make these to install these keys, and the manufacturers or the deployers can append keys, can append caveats and create a new macaron from that, and then grant them to a bunch of devices, and then the devices can directly use these keys to communicate with the controller, because that is basically a property of the macaron scheme itself. So session keys. So we make use of the JPEG algorithm to establish our session keys, and this algorithm is resilient to a bunch of attacks, and also provides for forward secrecy. This algorithm is basically used to generate high entropy cryptographic keys from a low entropy secret, which is the shared secret in our case. And this session key is basically used to receive the channel specific macarons or the attribute macarons. So this is the algorithm to actually generate our short-lived macarons, where we basically calculate the macaron. We calculate the key itself from the macaron. So first, the controller receives the macaron in plain text, which is the first line over here, and then the macaron is completely received, and it is used then to generate our key, and then the controller then generates a new nonce and adds a bunch of caveats to the macaron, and then gives the macaron back to the device, then gives the set of channel specific macarons back to the device. So how do these devices actually communicate with the controller later to actually receive actuator commands and send sensor data? So for that, the device computes the channel specific key using a method, and then computes the HMAC value for the data itself to provide for integrity checks, and then the entire packet is encrypted, as you can see in line 4, and sent to the broker, and then the broker forwards the messages to the receiver group, which is the set of devices that subscribe to the particular channel. So in our case, revocation is done by the technique proposed by Dan Boneh, and it is done. We basically make the keys short-lived, and they expire soon. The identity keys that are installed in the devices in the beginning during setup are the only keys that are long-lasting, and the channel-specific keys keep getting revoked after a fixed amount of time, after which the device has to renegotiate keys. And we also maintain a whitelist of all the manufacturer or deployer keys, and so that the subsequent macarons can be computed from them, and the session keys can also be generated from these verified macarons. So in terms of our implementation, we implemented our system in Ruby. So the web server is still a work in progress, and the web server is supposed to be there at the controller end. And we also implemented the client side algorithm on the devices, and we have a working system that we use the Mosquito MQTT broker to do forwarding. We use the ProVerif cryptographic verification tool to verify and prove that our shared secret that is used in the session key establishment is never leaked by our protocol itself. So the Goose protocol has a prescribed maximum latency of 4 milliseconds, and we set out with our system to try and keep our latency under that time. And when we were looking at previous work, they were all using elliptic curves, and then when we actually implemented when we actually ran elliptic curves on our devices, we found that it was way above the 4 millisecond latency that has been prescribed, and that was one of our motivations. And then we went off to then we tried our macaron scheme, and we found that it was significantly lesser than the allowed latency. And we also note that our implementation only requires additional 20 lines of code when it comes to adding our code to the clients, although the controller side has to be a fully functioning infrastructure, so we had to build that from scratch. But the client side only requires 20 lines of additional code, which is basically just a layer of crypto on top of the existing device clients. And most existing schemes talk about recreating the entire MQTT broker, but then our conversations with our industry partners told us that this is not a good investment of their time, so they thought that so our architecture would be a better fit because they do not have to re-implement the MQTT broker itself. So conclusions. So we basically built a system that meets our latency and security goals, and the tool is to be released soon in June, which is as per our timeline. And in terms of future work, we are going to integrate SSP21 into the shared secret option of, we are going to integrate our system into the shared secret option of SSP21, and we are already working with GRE to incorporate our scheme into their MQTT infrastructure. They are one of our industry partners, and we are also in advanced talks with some other potential industry partners. So that is it. Questions?
Does anybody online have questions? One more time in the room. All right, thanks so much. Thanks, Prashant.